For those of you that were absent today, you're going to want to watch this video, and you'll have all the stuff that was important that is going to be recorded on this video. And the first thing we talked about was quiz 3.2-2. It's posted, and the updates for the improvements, if you made any, are posted as well. So that is 100% complete now. So if you did really well on the first one and you got more than 50% on the second one, we're talking about quiz 3.2 and 3.2-2. First one was just plain 3.2. So that you will see those online. They got posted last night, and last night now would be Wednesday evening. This is Thursday, so you can look for those there. Okay, if you look at the do now for today, you're going to see a calculation, one for Boyles Law and one for Charles Law. And the way you figure out which is which is you get your little handout, if you'll get that out please. And we'll look at that here on video as well. Just a little handout. So you're only having to worry about Boyle or Charles, and it has to be one of those two that you're going to use to solve the do now problems. And all of your problems in tonight's homework will be done using Boyles or Charles Law. So we'll talk about those and how they relate to each other after I finish the stamping. In the meantime, you can literally plug and play these two guys. Now, I want you to look right here at something that you're going to have to be aware of, and that is that all gas laws, wherever you see temperatures, the temperature must be in Kelvin. It cannot be in centigrade. If you do it in centigrade, it won't work. You'll have it wrong, guaranteed. Okay? So, how do you fix that? Well, you simply go down to the bottom of the paper, and you'll see how that calculation goes. And down at the bottom, this is right at the very bottom of the second page. All gas law formulas require temperature to be in kelvins, and so you see this is your conversion. And if you did this minus 273 on, well, I shouldn't put that in parentheses, it looks like it times. Okay, it's minus 273 on that side, minus 273 on this side, and we wind up with degrees centigrade is equal to Kelvin minus 273. Pretty easy. Yeah. Okay, these gas laws that you're working with right now, today's stuff is really fairly simple and shouldn't give you too much trouble, if any. So in the do now today, we're required to give not only the name of the law but that is being used in A and B, but also you need to have the the actual calculation and solve for, in like letter A, you're solving for P2. In letter B, you're solving for T2. All right, that's it. What I'm doing right now is I'm blowing up a balloon. Okay, the balloon is about, what would you say, 5 inches in diameter going this way?
7.
6.
Whatever.
Purple.
Whatever it is, it's blown up about as much as I would blow this up without having it pop in my face. Now, the initial temperature, the initial pressure and volume is called P1 and V1. Now, what I'm doing is I am going to let some air out. The air go out. Now the balloon is considerably smaller. What would you guess that the pressure would be?
Smaller.
Smaller. Absolutely smaller. Because Boyle's law says that pressure times volume is equal to pressure times volume. First condition, second condition. This is second condition, and this would be P2 and V2, the smaller balloon. The bigger balloon is P1 and V1, core pressure and water. Okay? Now, the unit of measure for your answer here, what would you guess is going to be for letter A? Huh?
Torrs.
In torrs, yes. It'll be in torrs because the given is in torrs for P1. And in P2, using this formula starting with torrs, I'll get torrs at the end. If I started with atmospheres, I would get atmospheres at the end. Yeah. So you don't have to have the other stuff in any particular unit of measure as long as you're using the combined gas law or at this point, we're just dealing with Boyle and Charles. And you're going to figure out which is which. It won't be too hard. All of the formulas that you need for doing today's do now are on page 2 of the handout that you got yesterday in class. Okay, what's been done here by Arlene is that she has solved for P2 before she started out the problem. And that's legit. There's nothing wrong with that.
That's legit. That's legit.
That's legit, yes.
You got that on record?
Yeah, I got that on the recording. Okay, so now she's done is she's plugged in her numbers. She's got the mils right, and she has 700 for the temperature, and that's 700 in centigrade or Kelvin. Oh, wait a second. No, we're not doing temperature. I'm sorry.
Yeah.
No, this is fine. Okay. And then she goes ahead and solves. Is this number most people got?
Yeah.
Most of you got that? Okay. And so here's the number. What I like about what she has done, except here, she didn't give the pressure, and the pressure was given in mils, not mils, torrs. Okay. So we would want to see that in the unit of measure. What I was starting to say is I really like what she's done because she's shown the units of measure and how they cancel out with the mils and how they get left with the torrs. Okay, because torrs then becomes the unit of measure for the P2, which was the unknown. By the way, sometimes P1 can be the unknown. Doesn't have to be P2. Okay. The unknowns could be on either end. And I believe in that second problem, I'm asking you to find I'm asking you to find a T2, a second temperature. So that's good. Good first step. There you go. Let's go over here. Yeah. All right. And there, let's see, less, more. All right. That background will go away. Okay. I got it here. Here's our temperature at 700 degrees centigrade. And how did you change it into Kelvin?
Added 273.
Okay, 273 is added, and that's on page 2 of the handout from yesterday at the very bottom. And so that gets our T2 for us. T2, isn't that T1? You're supposed to find T2.
Yeah.
Okay, so it can't be T2. Okay, this guy cannot be T2. Oh, find T2. Okay, so I'm sorry. I apologize. So this is the correct guy. This is where you plugged it all in. I thought this was supposed to be equal to this, and I read it wrong. Okay, so this is fine. This is perfect. He's showing the units of measure in every place that he's got a number. I like that. That's excellent. That's the way it should be done. Why? Because especially if you get the 1 and 2 mixed up, okay? Back to the balloon. If you use the pressure from the smaller balloon with the pressure of the bigger balloon, you've just inversed or reversed. You've come on. Yeah, you got a problem. You're gonna make something that's a direct relationship an inverse relationship, and that will definitely give you the wrong answer. So the only thing I'd like to see you do is I assume this is your answer here. And is this 1237? Really? Is that big? Is that what the rest of you getting? Oh, okay. Didn't realize I had a pump that high. All right, good. Excellent. Let's give you a stamp for that. Okay, the question was, how do you determine what the initial and ending conditions are, and how do you keep them together? So we're looking at number 1 on page 422, part of your homework. And what we're seeing is that it says, and these are the operant words, and you want to write them down in your journal today. These are excellent. Okay, the volume of a gas at. The word at tells you that's one of the conditions. Okay, at 99.0, kPa's is. At and is, tie those two guys together. So now we're looking at volume, and the volume one is equal to 300 mils. Okay? Now, what's pressure 2? Okay, now, is increased. That means we're going to a new set of conditions. So the increase is an operant word. It tells you a new condition is going to occur. And that is equal to 188 kPa. All right? And what does it want? What is the new volume? Well, new volume is volume 2, and that is your unknown. Plug those numbers into Boyles Law, and it works. That's all there is to it. It's really simple. This is something else we discussed in class today, which is very important. If you have not signed up for my YouTube channel, or if we could not find your username, you can come to me during class or after class, before school, break, or lunch, and show me on your own phone, if you can go online on your phone, if you have internet on your phone, or on my computer. I'm fine with that. I'll have you sign into your account on YouTube. When you sign on to your account on YouTube and you look for the channels that you are subscribed to, that is easy to do, and my name, O. Wigger, pops up there, you have your 2 points. Okay? You have till Friday to do that. After that, you will get 100 sentences every day for as long as I do not have you signed up on YouTube. I am. Thank you. That's exactly what I'm doing. And you are being told well in advance, folks, we are talking about something that takes all of 3 minutes. This is not a difficult challenge. I know it's only 2 points, but this is 2 points that you have to get. Why? Because it makes you the recipient of or notification at least, of every time I make a new video. And I made 2 videos yesterday. And on your channel, you will see that I made 2 videos yesterday. And you can go to my channel and look at them. Because if I made a video, you need to watch it. Because it has stuff on there that you will need to know. Okay? Something else. I don't care how, guys, I don't care how you wound up with no credit. Okay? Bring me up the little slip that you have, Mr. Wigger. I'm on. I'm signed up. It shows it right here. Problem solved. I will write 2 points on your little piece of paper. I will take your little piece of paper and I will record it in my grade book, and then you don't get sentences every day for as long as the rest of the semester is, until you get signed up for my account on YouTube. Okay? Now, let's look at this little guy. We are talking about today just Boyle and Charles. How do I know the difference between an inverse and a direct? You'll notice that I've written those in there. How do I know the difference? Can anybody raise your hand? Tell me if you can see how I know that the Boyles Law is inverse and Charles' Law is direct. Yeah, Moses? I'm sorry, what? No, absolutely not. Nothing to do with it.
So in the equation is stated.
It's the way the equation states it. Yes. What is it that makes it direct? You guys whisper, or you're both getting sentences. Yes. Okay, when both sides of the equation, now I'm looking up here at this guy, okay? Both sides of that equation are side by side, okay? Multiplication on both sides. That makes an inverse relationship when you have multiplied factors on two sides of an equation, of an equal sign, okay? And likewise, for direct, division on both sides makes those guys direct. So as volume goes up, temperature will go up, and vice versa. If they go down together. Now, I have nice little links here on tonight's homework page, as well as here in the notebook file. And let's take a look at a neat little animation of Boyle's Law. And here's what it looks like. It's not an animation, it's actually a little, what do they call these? Applet. That's an applet, and you can work this applet and actually see this relationship. Over here, you'll see a graph. You see that little graph there? All right, and when I do this thing, it is going, that isn't a graph, but it's going to plot and make a graph. Let's take a look at this guy. I'm going to hold on to this plunger by click and hold, and then I'm going to move it up, which is reducing the size of the chamber. What's happening to the pressure as I reduce the size of the chamber? Yeah, it's increasing. Okay, what is that, direct or inverse? That's inverse. Yeah, one goes up, the other goes down. Yeah. So when I pull this guy back out, it brings the pressure back down. I can record, by the way, on this applet, I can record at any point. So let's check this out. Here's my starting. This is considered to be normal pressure at 1 atmosphere or at sea level. Okay, so here we go. I let go of that, and it recorded. I wasn't all the way out, I guess. I guess I was all the way up. Anyway, at this particular volume, at 40 mils, I had a total pressure of 12.86. So let's watch and see. Does this actually show inverse? Inverse, one goes up, the other goes down, right? Okay, I'm putting down the volume. The volume is down now, and you'll see a lesser volume and a higher pressure. Cool, huh? And if I go ahead and hit the graph thing, you'll see the graph here of the 2 points. Let's see, delete the record. Where's the other point? Let's see the 2 points. What? Oh, there it is. Okay, here's my 2 points. And if I make it in, see, this is assuming that pressure versus volume is direct, but it is not. 1 over P is equal to V, and that gets our 2 dots. Where's that other dot? There should be a second dot. We should go in a straight line. Yeah. Well, anyway, that's just showing you the inverse relation. I don't know why the graph isn't working right, but I'm not going to mess with that right now. Now let's go back and close this out, and let's look at Charles Law. What kind of a contraption do you think they'll have for a Charles Law? What's the variable? 2 variables. Okay, so volume, they've got to have a little plunger of some sort, right? Because that's going to be the variable of the volume. And then what are we going to do to change the temperature? Well, there's going to be a thermometer there somewhere, yeah? Forget about Kelvin for right now, but yes, you would have to have it in Kelvin. Temperature will be read in Kelvin. What kind of a device do we need to be able to change temperature? No. What do we need to change that temperature? What? Heat source. Very good. Heating source or a refrigerator. Right? Right? We got a refrigerator to bring it down. Or just let it equilibrate or form equilibrium with the outside environment. So let's see what this little guy looks like. You're going to have something there in your head about it, and this is what he looks like. This is really kind of neat. Watch this. I'm going to bring the temperature down, which means I have a cooler in here. So if I bring the temperature down, what's going to happen to that volume? Okay, let's watch. Here we go. See the plot? we're getting a plot of what's going on. You see the little plunger going down, don't you? Isn't that cool? Little plunger's going down. It is definitely decreasing. Okay? And you'll notice it comes down slowly because any heating or cooling device isn't going to make it happen immediately. So this is really kind of realistic. Okay, and now we're down to 184.14 or whatever. And now let's move it back up and let's see what happens. Okay, what's your prediction? It's going to go up. You bet it is. And there you go. And now you see the plot moving up. It's a straight line because they are directly proportional. Okay, temperature's going up and the volume is going up at the same time. Very cool stuff. I think it helps to have did you hear that, Adita? Okay, anyway, we got that cool. Remember again, the temperature for Charles and every other gas law that has a temperature in it is going to be in degrees Kelvin. If you do centigrade, it is not proportional because degrees Kelvin relies on the fact that all motion stops at 0 degrees. Kelvin, not centigrade. Okay, 273 degrees difference between centigrade and Kelvin. So if all motion stops, you can't go down any further. So if you start there and go up, this was a big problem for the scientists that originally came up with Charles' law, was just grappling with this issue. It's not directly proportional, but it ought to be to temperature. It's kind of weird. What's going on? And finally somebody realized if we deal with Kelvin degrees, it is proportional. So all gas laws are proportional in Kelvin degrees. Okay, that's it. And what I had everybody do at the end of class is write a journal. So get out some paper and write your journal.